All right, everybody, welcome to ZeroAvia booth here at the show. We're doing our third live stream right now for the live audience and also whoever we have at the booth. I'm founder and CEO of ZeroAvia, Val Miftakhov, and we've been at this journey for about 5.5 years. I started a company 5.5 years ago to transition aviation market to the new future, to zero emission propulsion. We think that the way to do it is to create new types of engines for commercial aircraft, and we think the right type of technology for that is hydrogen electric. Hydrogen is the best energy carrier for aircraft. It's 3 times better energy content on a per kilogram of weight compared even to jet fuel. So as opposed to batteries, for example, hydrogen is 3 times better versus batteries that are 30 to 50 times worse in terms of energy content. So hydrogen is really the best way to get enough energy on board the aircraft and then convert it into propulsion. We think that the best way to do it is through electric conversion, taking hydrogen, moving it to the fuel cells, and then producing electricity from the fuel cells, and then running electric motors with those electric energy that comes from the conversion of hydrogen, and those electric motors then rotate the propulsors, propellers in small aircraft, and then fans in large aircraft. So familiar jet engines are really enclosed propellers these days with large fans producing most of the thrust. So that's how we're approaching the problem. And I started the company because I saw the need in transforming this industry. This is quickly becoming the largest problem that we have in sustainability. My previous company was in the sustainable transportation space as well. It was in the electric vehicles. We built the world's largest network of smart charging stations with the idea that the charging infrastructure and infrastructure in general, the energy infrastructure, is one of the main problems in transforming these large transport industries. We've built that in the previous company. The company was acquired 5.5 years ago, and that's when I started ZeroAvia. With ZeroAvia, we are looking at transforming all segments of commercial aviation to the new future. This starting with small aircraft, as you can see in our booth here, 600 kilowatt systems going into 10 to 20 seat aircraft, and then progressing to larger and larger aircraft. Here we present some of the roadmap from 2025 first launch to 2027 larger aircraft, 40 to 80 seats, and then going to regional jets and then large jets as well. We already announced at the show on Monday results of some of our partnerships with Mitsubishi Heavy Industries regional jets, where we've confirmed the possibility of regional jets going hydrogen electric with the fuel cell technology. Over the last 9 to 12 months, we've done great analysis with the manufacturer, about 1,500 aircraft flying today, CRJ family, and we now know that we can convert that aircraft, can enable that aircraft to work with hydrogen electric engines. So this is one of the first studies, proper detailed studies that we have done with the airframe manufacturers that confirm large aircraft can move to zero emission propulsion with hydrogen. We of course have also partnerships with other airframe manufacturers. For small aircraft, we have partnership with Textron and de Havilland Canada, respectively Cessna vehicles and Twin Otters. For large propeller planes, we have partnership with de Havilland Canada as well. So for first 3 segments, we have partnerships with the major airframers that are looking to bring our technology, our engine technology, to the markets. So over the last 5 years, we really saw the huge progression from people talking about offsets and maybe some sustainable aviation fuels going all the way to hydrogen electric propulsion. And now with Airbus, Embraer, a number of these other manufacturers firmly going to hydrogen as the main fuel of choice. We think that transformation is in the making, and we're looking to drive it. So this show was already a great success on the commercial side for us. We have announced 100 production slots bookings yesterday with Monty, which is a major lessor of small aircraft. So this is now booking specific production slots on our production lines. We already have about 2,000 engines on pre-orders, and now we have specific production slots being booked out. This creates a sense of urgency for the industry as well. Who's going to be the first to operate these engines? Who's going to be the first true zero-emission operator? And we really welcome our customers and partners to this journey with us. So with that, I'll take some questions, maybe from the audience here or from the live stream.
How many flights have you done so far? And what was the longest flight you did?
The question is how many flights we've done so far and what the longest flight we did. So we've flown 3 prototypes to date. The first prototype we flown back in California in 2019. I was a test pilot back then for the aircraft, so something I'm not doing anymore. But the latest prototype that we have is an aircraft called Dornier 228. It's a 20-seat aircraft with full-size engine, full-size aircraft in our first segment. We've done 9 flights, I believe, on that flight test campaign to date. First flight was January 19. And then since then, we've done 9 flights, expanding the envelope, altitude, speed, and duration of flight. I believe the longest flight we did is around 20 minutes at this point. We are looking to, as the next phase of the flight test campaign, where we'll be expanding into A to B flights. So to date, we're flying all around our airport in Cotswold Airport. The next set of flights will be from A to B, and we're looking at various locations now for that. So that's coming up hopefully later this summer.
And when will you fly with 2 engines on hydrogen?
So for this specific, the question was when we will fly with 2 engines on hydrogen. So for this specific aircraft, test aircraft, the plan is to keep it on the turbine plus the hydrogen electric engine. The next small aircraft, test aircraft, will likely be our launch candidate, which is likely going to be a single engine aircraft. So Cessna Caravan is one of the top candidates there, and that will be the next flight vehicle in the small segment. Yes?
I know that weight is one of the challenges. Do you have any plan to reduce the weight, like storage or fuel cell?
Yeah. So the question was how challenging is the weight of the system, or weight for the aircraft enabling? Yes, weight is a challenge. Main challenge, well, actually, for small aircraft, in both ways, in 2 ways. One is on the power plant itself, the engine itself. The engine is heavier than the turbine, at least the first iterations of the engine. We do have roadmap to get to parity within the next, let's say, 3 years, 4 years on the development cycle, and then a couple of years for certification. So the first variant of the engine will be heavier than the turbine engine. So we do have some weight penalty there. What we do with that is we effectively trade some of the weight for range. So for a small aircraft like Cessna Caravan, for instance, instead of having 700, 800 nautical miles of range, in first variant we're going to have maybe 300 to 400 miles of range. And the reality is that these aircraft are used for missions all within that range limitation. Right, so typically 1 hour or less type of missions, 100, 200 miles. In fact, the average is somewhere between 150 nautical miles and 200 nautical miles for that type of aircraft. Shorter for the passenger transport, longer for cargo. But in all of these cases, it's safely within 300, 400 nautical miles. And by the way, when we quote 300, 400, that's with reserves, right? So there's 45-minute reserves on top of that, so that we can have proper commercial operation, IFR reserves. Yeah? Okay. Yes?
Do you think that the procurement of hydrogen will be an issue for you at the time of entry of service of your aircraft?
Yeah, question was on the procurement and availability of liquid hydrogen at the time of launch. So for the first vehicles, for the small vehicles, we are looking at gaseous hydrogen as the carrier, energy carrier. So that is a much simpler problem to solve, and also we are able to put in production of that fuel relatively easily at even at low volumes to the airports, to the sites of operation. For larger aircrafts like this Dash 8 or ATR aircraft, for example, that is our next segment. We are looking for liquid hydrogen as the fuel storage form. But those aircraft are launching at around 2027 for us. So we think that that's enough time to get the liquid hydrogen storage technology matured, and also to get the economics of production of liquid hydrogen to the right place before launch. For the small aircraft like the Cessna Caravan, we think that at launch in 2025 and subsequent scale up in 26 and beyond, we will already be at break even with jet fuel. The break even cost of hydrogen is about $6 a kilo, which we already have contracts for that. We already have shown that we're able to produce hydrogen on site through electrolysis from local renewable power at those levels of costs. Okay, with liquefaction, with liquid hydrogen, you have some additional costs coming in, and also the stock turbine engines are a little bit more efficient than they are for small aircraft. So the the break-even cost of hydrogen is lower than what you would have for small aircraft, but we'll get there by 2027-28 when these larger aircraft are in service. We also get to break-even point. Yes.
When you're talking about business jet, the passenger is around 4 to 6 or 7. Do you think your system will overtake the conventional gas turbine engine?
Yeah, so the question was for larger aircraft, larger passenger aircraft, do we think that this approach, hydrogen electric approach, is meaningful and will take it over? So I think over time, this technology is applicable for all sizes of aircrafts. It will take probably about 10 years for this technology to be, for us to get to the engine size that's applicable for a single aisle aircraft. As I mentioned, we've done the work with Mitsubishi on the regional jet side. We think that we will be able to bring that level of power to that type of airframe, so sub 100 seat regional jets by the end of the decade. Yeah, but the single aisle, so larger aircraft, so the 737, A320, that's probably 10 years out. And we already started some conceptual work on that, but no real program yet. So we do have 2 programs now. That one is for small aircraft and one is for larger sub 100 seat, covering both turboprops and regional jets. Yeah, of course.
Very interested in this system. So about the reliability. So usually typical technology, the electrical parts are less reliable than mechanical parts, in my experience. So how would you, having this type of electrical system, how would you try to get to that level of safety criteria from the FAA standpoint, certification standpoint, like -9, -6? How do you try to get to that? Do you have any plan for that?
Hey, so the question was, how do you get to adequate reliability at or above the level of the conventional aircraft?
Say your system is not reliable. That's something wrong.
Yeah, that's but we have to show that it's meeting or exceeding the current technology. Yeah, and definitely we have planned for that. In fact, making some parallels with other industries. So in automotive space, you actually see the higher reliability of the electrical systems, electric propulsion systems, compared to the internal combustion engines already. Right now, in aviation, a little bit different comparison. You have turbine engines that are the same type as the automotive engines, but we think with the electric propulsion you can actually get even better reliability. So especially for small aircraft engines, small turbines, like for example Pratt & Whitney P26 engines that are powering these vehicles like Cessna Caravan. Your typical maintenance cycles are about 2,000 hours hot section inspection, 4,000 hours or below, full engine overhaul. And we already see with the fuel cells, the types that we are using for small aircraft, already seeing 20,000 hour time frames for a longevity of the fuel cell stacks, right? And fuel cell stacks are likely to be the sort of the critical path components that would need to be replaced first, because the rest of the system, power electronics, electric motors, we expect them to have even longer overhaul cycles, if you will. And we're already doing the tests, durability tests in our labs, and a number of other people do durability tests for these technologies in some other applications. And like for instance, for heavy duty ground mobility trucks, for example, already people have confirmed 30,000 hour duration for the fuel cell stack control. Aviation is actually an interesting use case, because even better use case for this, because your power profile is much more stable than in automotive. In automotive you have a lot of start-stop type situations. Also the air quality is generally lower because you're right at the ground and you're subject to all the dust and the particulate input. In aviation, you set the power level, and most of the flight goes through just a very small number of power levels, and that helps the fuel cell system to operate optimally. Yeah.
Question about your report with Mitsubishi. On the scale from 1 to 100, how far are you now in that program? You need to do probably 2000 RJ version engine for that. What has to be done? Which boxes do you have to tick?
Yeah, so the question was with the Mitsubishi program on the scale of 1 to 100, which is an extremely precise scale, where we are towards the actual introduction of the product, yeah? I would say at this point we're at maybe a 9 or 10 out of 100. Yeah, so lots of work remaining. But what we were able to achieve is that we have confirmed the feasibility of this, right? Because this was a big question. It's a large aircraft. It's a high-performing aircraft. It's not a propeller aircraft, right? So that's quite a few differences. And we were able to confirm that we are actually able to build a commercially viable vehicle. So it's not just about can we get the aircraft up in the air, it's also about, well, how many seats you're going to have, what the economics of operation is going to be. Can we refuel it in a reasonable amount of time? So we looked at all those parameters, and we said we can make an economic aircraft out of this. So that's a significant achievement, but it's just the start of the journey, fuel, right? So, and it will use a variant of our ZA2000 engine. The 2000 in the name of the engine is for the minimum power level. So that's effectively a modular engine. 2000 kilowatts or 2 megawatts is 2 modules strung together, producing about 2 megawatts of shaft power, and then we can scale that to about 6 megawatts. And that's the upper range of that is what would be used for the regional jet application.
For that you are using the high temperature version, HTPM.
Yeah, for that we use high temperature fuel cells.
How difficult is it one? Because your colleagues from Universal said, well, they might succeed, but it might take a long time to develop such an engine and to get to a mature level.
Well, so we already have, on the high temperature fuel cell side, we already have substantially the type of technology that we're looking to scale to that level operating in our lab. So we have pressurized high temperature fuel cell stacks already operational and being under test right now. And obviously there is a roadmap there that gets us to the point in both scale and the performance that we need to get. We need about 2.5 years to get to a design lock on those. So obviously we are much closer to the design lock on the small engines that are based on low temperature fuel cells. But the high temperature fuel cells were about 2.5 years away. And that feeds into the launch timeline of 2027. Yeah. Good.
About the hydrogen storage on the airplane. So we did some study about the hydrogen airplane before in our company, and the largest sort of challenge that we had was also weight, but also hydrogen storage. How would you store that? And it's almost like the hydrogen can, which is so big that you have to make a fuselage slightly size. So it's almost like you're carrying hydrogen fly rather than carrying passengers. So do you have any roadmap for that hydrogen storage and how that tank is moving?
Yeah, so the question is, what do you do with higher volume requirements for hydrogen storage? Yeah, so a couple of things there. Hydrogen does, as I mentioned, 3 times better per unit of weight, but about 4 times worse on the volume, right? So you need higher volume to store the same amount of chemical energy in even liquid hydrogen. So that is a challenge. Now, 2 ways we're solving that problem. One is the hydrogen electric engines are actually significantly more efficient than a turbine engine. So if you take the turbine engine and just convert it to hydrogen, you're going to operate with roughly the same efficiency, maybe actually even lower efficiency than what you can operate on kerosene. The reason it might be lower is because you cannot really operate at the optimal fuel oxygen mixture because the temperature, flame temperature is too high, and you will produce a lot of nitrogen oxide as well out of the engine. So there are some difficulties operating hydrogen combustion engine, but at best you will be at the same efficiency. And that's for small aircraft, the 10 to 20 seat aircraft. This is 20-25% of the small turbine. For larger propeller planes, this is maybe 25-30%. The fuel cells are operating at 50 to 60%. So you can have a 2x efficiency improvement, which means that you need 2x less fuel, right? So you had a 4x disadvantage coming in. Now you reduce that to 2x. Now, so you have significantly lower excess volume requirements than you had in the beginning. And that's why, by the way, we think that hydrogen electric fundamentally is best approach, because in addition to all the other factors, it also requires half the fuel that you would need to run in a hydrogen combustion. And that's, the cost advantage is there, but also volume advantage is there. The second part of the equation is actually, you can find enough space in the aircraft if you want 2x the volume of storage, for example, right? Yes, you would be taking some spaces that you are not taking today, but a typical aircraft, commercial aircraft, you look at the aircraft, and if you think about the percent of volume that is used for fuel storage, it's quite small, right? Typically, around 5% of the total volume of the aircraft. By weight, it's significant, right? By weight, 20-30%, but the fuel is dense. So you look at aircraft like this, all the fuel stored in the wings, that's not a lot of volume. So at the aircraft level, you can go from 5 to 10% and not introduce significant drag or significant sort of internal volume. If you're talking about 4x, then you start getting into larger numbers. So that's sort of how we think about it. Yeah. And then for some of the aircraft, like for instance this propeller, I'm pointing to the if it's not in the camera, the 400, the Dash 8 400, which is an 80-seat aircraft. It's designed in the 90s, and back then they were flying longer missions than today. The aircraft is designed to be a 1,500 nautical mile max range. Propeller aircraft, 1,500 nautical, that's 7 hours in the air. Obviously today, nobody flies that aircraft for 7 hours, even cargo operations, right? All the missions, and we looked at all these parameters, all the passenger missions are generally sub 300 miles. all the cargo missions are sub 500 miles. Yeah? So you need less than half of the max range. Now, if your penalty on volume is just 2x, but you need half the range, you're back to the volume that you started with, right? And then there is a challenge, of course, with wet wings and sort of liquid fuel like kerosene, you have a lot more flexibility. You can put them in thin spaces, right? So you have that limitation. And we've looked at that with Mitsubishi, for instance, right? Looking at the aircraft, we cannot use outer tanks, for example, in the wings, right? Because the spacing is insufficient. But you can use the center box. You can use some of the inner root tanks. So with that efficiency improvement and the sort of practical range, yeah, you can get it. Okay.
We're gonna wrap it up there.
All right. Excellent. Thank you, everybody. Yeah. And for those who are online, visit our booth here in Hall 5, ZeroAvia. Thank you.